Finally, a real advertisement. I have 2 books. This book is on Introduction to Quantum Computer. This is about algorithm. You will learn the basics of up to Shor's algorithm. You'll understand how the qubit evolve. And this one is the hardware for engineer. Because I'm an electrical engineer, there are lots of physics that we did not cover in our curriculum, so I try to give the basics. And this one covered the superconducting qubit and silicon spin qubit. And this one, I'm writing a 2nd volume, but I put it directly on archive. Now it has the trapped ion. I plan to have neutral atom and photonics in half years. I also have a YouTube channel, and here is the class for the algorithm class E225, and this is for the hardware. And if you're interested in any of these, please send me an email. I can send you the link. Okay, so thank you. So I will go directly to what is a quantum computer. You all know that quantum computing is very important because it uses 2 important phenomena. One is called superposition, one is entanglement, right? We all know we are already using quantum mechanics, but in this so-called quantum 2.0 version, we use superposition and entanglement to do computation. And actually, we also need to use the interference of the quantum states in order to get the result. So there are mostly 2 types. One is gate-based quantum computer, and other is quantum annealing. This shows the quantum circuit of a gate-based model. It looks like a classical circuit, but later you will see that it's not exactly the same. And quantum annealing is just an optimization. You try to map the optimization problem to a quantum landscape, right? Some quantum device, and then let it naturally optimize through physical interaction. In this process, you might even have tunneling through this configuration space. Company like D-Waves, if you have heard of that, use this. It has many applications for material design, computational, fluid dynamics, secure communication, financial service, quantum machine learning. In one word, if it works, as you know from news, it's going to be game changing, right? But now it's still not working. That is the caveat. So what is a quantum computer? Let's start with the classical state. You all know what it is. We represent information 0 and 1 by classical means, head and tail, happy or sad, or the on-off of transistor, right? So information are represented by state. Now, in quantum computer, it also has some, we call it basis states or classical states or whatever. We still can represent 0 and 1. Here we put in the so-called bracket notation. You can ignore it. It's just a way to represent the state. Right, if we only work with this computational space or the classical states, classical states or basis states, probably we can also use coins, head and tail, happy or sad, or on-off a transistor. That's no different at all. So quantum computer is not anything. It's not something completely different from classical computer, right? The only difference is that besides working on this 0 and 1 state, we can compute with something called superposition. So we are allowed to have a state that is a superposition between 0 and 1. So you have a part of 0, a part of 1, right? Sorry, there's some problem with the display. If from a coin perspective, this is a wrong analogy, but it's a pretty good intuition. It's just that you have a coin spinning on the table. That is the state of your qubit, and you don't know whether it's head or tail, right? So it's like alpha of head and beta of tail. And that is the main point. Quantum computing is powerful because it can use superposition. Now this is 1 qubit. As you can see that to describe a state, I then need 2 compressed number alpha and beta. So it compared to one classical bit, it has more information, right? You can store more information if we treat it as a quantum memory. Just 1 qubit, we can store 2 compressed number in this sense, right? What if I have more qubits, right? This is a classical one, you know very well. I have 4 classical bits I can store from 0000 all the way to 1111, which is 16 states, and that's all you can store, right? Now, the same as I said, quantum computer is the same as classical computer if you only work on the classical state. So if I have 4 quantum bits, 4 qubits, I also have 16 basis states, right? Which is which is 0, 0, 0, 0 all the way to 1, 1, 1, 1. Just like in the 1 qubit case, I can have 0 and 1 because the classical basis is 0, 1, right? Here I have 0 to 15, then so I have 0 to 15. So now it means that to describe this 4 qubit state, I need 16 compressed number. Or thinking in other way, just like that, using 4 qubit, I can store 16 compressed number in that sense, right? It's pretty big. So if I have n qubit, then it means that I have 2 to the power n basis state. So to describe a state, I need to describe 2 to the power n compressed number, right? And now you see that this is exponential. Why? For example, if I have 300 electrons, spin qubit, let's take it as an example, then it has 2 to the power 300 basis states, as you all know. And that means there are 10 to the power 90 compressed numbers that is needed to describe as the state of 300 electrons. Counting 300 electrons is so easy, just 300. But we need 10 to the power 90 compressed numbers to describe it. So we still have not talked about the power of superposition yet, but I hope that from here you already see that it's profound, right? If we are able to use it as a memory, store lots of stuff just using 300 electrons. Of course, we cannot use that in that way, but it has a lot of information because the total number of storage in this world is less than 10 to the power 21 bytes, and number of atoms in the universe less than 10 to the power 82. Right? So this one shows you why it's profound, because we can do superposition. Now, quantum mechanics is linear. If I try to apply a function to it, right, hand-wavingly, right, this is a superposition of 4 basis states. So this is 2 qubit because it has 0, 0, 0, 1, 1, 0, and 1, 1 basis state. Then it means I do the computation to each of these basis states at the same time. And this is true, and of course it's a lot of philosophical debate, but it is true that we can do this quantum parallelism. Some people may say, oh, it looks like we have a parallel universe, but it's true that everything everywhere at once if you apply this function to it, right? So here you can feel that, well, if we can make it superposition, if we do it right, we can do parallel computation with one single copy of hardware. That is very important. We are not having multi copy of hardwares. Okay, so we know superposition is important. We do need to understand a little bit something about quantum mechanics. You probably know that already. It's about measurement. Let's go back to the analogy of a spinning coin, right? How do I know that whether it's head or tail, right? You say that it's a superposition of head and tail, so let me measure it. What do? Stop it, right? So it will collapse to either head or tail. And that is the same for a quantum state. It is a superposition of 0 and 1. How do I know whether it's 0 or 1? Well, measure it, right? There are many different measuring methods. Then it will collapse to 0 or 1. It's completely random, right? So, and that's why Einstein said that God doesn't play dice, because he doesn't believe that the nature is completely random. So this is completely random. So two things. One is that you lose your state when you do measurement. It collapses to the basis state 0 and 1. And the probability that you will collapse to 0 or 1 is proportional to the square of the magnitude of the coefficient in front of it. Okay, so if you have larger portion of 0, then you have a higher probability to collapse to 0. Okay, so this is very important, that it collapses, you lose your information, and then it collapses randomly to 0 and 1. So we understand measurement, we understand superposition. Then let's talk about something called entangled state. This is a very important concept. We don't have time to go into details, but if you try to treat it as a simple multiplication, now I'm showing you a state that is that of 2 qubits. Why is 2 qubits? Because you see that it's a linear combination of 4 basis states, right? The basis state, as I said earlier, just same as the classical state, 0, 0, 0, 1, 1, 0, 1, 1, but it's a linear combination or superposition of it, so it has a coefficient of 1 over 2, negative 1 over 2, 1 over 2, negative 1 over 2, right? If you multiply into it. So this is alpha, beta, gamma, delta. It's just the same as the concept in 1 qubit. Now, these two written basis state, you actually can factorize it. For now, let's just Assume it can be done that. This is like linear algebra, something called tensor product. You don't need to worry about that, but you just trust me. It's just like factorization. I can factorize it into two subsystem, right? For example, if you try to check 0 times 0, 0 times -1 give you -0, 1, 1 times 0 plus 1 plus 1, 0, 1 times -1, -1, 1, right? So basically it's saying that, hey, yeah, you have two electrons, they are whole system, but they are not entangled, because I can describe this whole system by individually describing each subsystem, right? So this is the wave function or the state of electron 1. This is the state of electron 2, and this is also the tensor product give the combined state of the whole system. Now, however, in quantum computing or in quantum mechanics, there are some states you cannot factorize them no matter how you do it. And this is very important because entanglement is something, if you plus something called long-Clifford gate, is something cannot be simulated efficiently by using classical computer. So I forgot to say that for any unentangled state, you can simulate it or compute it easily, effectively using classical computer, right? So if you don't have entangled state, basically you are just doing something can be done by classical computer. And that's why entanglement is so important from algorithm perspective. Another perspective is something that challenge our intuition and what Einstein called the spooky action, right? We can show it. For example, if I have two electrons now, I put it in entangled state, right? This is the same as this state. Although I call it 0, 0, 1, 1, but now I call it spin up, spin up, spin down, right? So it is thing, it's just a name, right? So they are entangled. Why they are entangled? Because you can see that whenever the first electron is spin up, the second electron is also spin up, right? When it is spin down, it's also spin down. And it is their true state is a superposition of both of them. I don't have a spaces that is spin up for electron 1 and spin down for electron 2, because that spaces has a coefficient of 0, so you don't have that chance. Now, if I move one electron really far away to 100 light years away, and I assume they are still entangled because if there's no noise, I do it very well. I have a perfect perfect channel, right, for optical communication. If it is photonics, I have a perfect fiber, for example, right? They're still entangled, so this is still the state to describe these two electrons. Then I try to do a measurement on Earth. Now, as we said earlier, when you do a measurement, what will happen? The state will collapse to its basis state. But now this is a 2-qubit electron, right? So you will collapse to either up or down, because this is a basis state, right? So assume that, so it has 50% chance for the one on Earth to collapse to up, right, or collapse to down. 50% chance, right? So let's say it collapsed to up. Because the whole system will collapse at the same time also. The electron 100 light years away will instantaneously collapse to up also, right? So this is something a little bit spooky, although after more discussion or proof, you will find that this is not really that spooky. But the point is that whatever happened in Earth will happen 100 light years away immediately, instantaneously, even faster than the speed of light. It looks like faster than the speed of light. And that's why it shows another specialty about entanglement. We are not trying to prove anything, but just want you to feel that entanglement is important, right? But if you go through all the reasoning, you will find that you still cannot transmit information faster than the speed of light. But this is something later lead to the Bell's inequality and then the violation of Bell's inequality, and to prove that quantum mechanics is really different from classical mechanics, and that resulted in Nobel Prize, right, in 2-3 years ago. So okay, so I go pretty fast, right? But again, what is quantum computing? You use superposition. The measurement is special, and you need entanglement, right? Even you forgot exactly what they are, but these are the 3 main points. So now these are the qubits. They're boring qubits. They're just the spin of electrons sitting over there, a transmon qubit, superconducting qubit sitting over there, and that's it. And you will know that, yeah, every atom, every object can be described by some wave function, right? So how do we make a quantum computer? Then we need gate, right? So what is a quantum gate? So I just want to say something called broad sphere. So if you have one qubit, how do we describe it? How can we visualize it? We can map it mathematically to a sphere in the 3D space. So this is very important. We are not really, the qubit does not reside in our 3D space. The state does not reside on the 3D space. For example, here you will feel that is pointing up is 0 state, pointing down is 1 state. In our classical vector, in our 3D space, pointing up plus pointing down should be 0, right? But no, but this is not a real 3D space. So 0 plus 1 is not 0. It's just a superposition of 0 and 1. So I want you to be careful about this broad sphere concept. But anyway, every point on this broad sphere represents one quantum state of a qubit. Then what is a quantum gate? Quantum gate is nothing but just to change the state of the system, right? And so you're just rotating on this broad sphere if it is one qubit. If it is multi-qubit, you cannot see on broad sphere, but it has its hyperspace. It lives in its hyperspace, and it is still rotating in the space. Okay, so it's just a rotation. And how do we make a quantum gate? We usually depends on the physical system. Can be a laser pulse or microwave pulse, right? That you shine to it. For example, if it's a spin qubit, we have actually a AC current, and it will create a AC magnetic field, and then it will change the state of the spin, and then it's just like you are rotating on the broad sphere. So that is very important because in our circuits, every gate occupy an estate, right? An area. If you're 1 trillion gate, you need a larger silicon chip. But this is not the case. You have 1 trillion gates, you only need to shoot 1 trillion laser pulse or 1 trillion microwave pulse. And there are different gates. Some gates are the same as the classical counterpart, like NOT gate and control NOT gate. I won't go into details. But some doesn't have a classical counterpart, for example, superposition, like Hadamard gate. For example, if I start with a 0 state, this is the classical state, right? I apply the Hadamard gate, it becomes a superposition of 0 plus 1, right? This is impossible in the classical quantum computer. So at this stage, I want to emphasize that we should be able to build any 1 qubit gates to rotate on the broad sphere, and also one so-called entanglement gate. One example is the control NOT gate, because any quantum circuit can be decomposed into these elementary gates or approximated by these elementary gates. So if we can implement arbitrary 1 qubit gate and have one entanglement gate, then you will be able to implement any quantum circuit. And then that is a useful quantum computer. So that's why I want to spend a little bit time on this control NOT gate. This control NOT gate is nothing special. It works like a classical control NOT. So what does it do? Again, we will only look at this part because this is just a general formula. For 2 qubits, we have 001010 and 000110 and 11 as the basis state. Remember, right? Because every quantum computer, if you have 2 qubits, you have 4 basis states, because these basis states are just the same as the classical bit, right? But then you can form a superposition of it. So we only need to see how it operates on this basis state because it's linear. So control NOT is nothing but just say that if the first qubit, which is the control qubit, is 0, do nothing to it. Then it means that 0, 0 is still 0, 0, 0, 1 is still 0, 1. If it is 1, then you apply a NOT gate to the second qubit. So because it's 1, 0, so it is 1. So I apply a NOT gate to the second one, it becomes 1, 1. Right? It is 1, 1 here, apply a NOT gate to the second one, it becomes 1, 0. And that is the so-called control NOT gate. And we call it entanglement gates because we can use it to create entanglement. And this is an example of entanglement. We start with 0, 0. Earlier I told you that I can have a Hadamard gate. Hadamard gate will what? Do superposition, right? So 0 will become 0 plus 1. That is how we do it. For B, for the lower qubit, nothing is changed because there's no gate. You can do a distribution, just like what I told you earlier. This is just like a multiplication. 0 times 0 becomes 0, 0. 1, 0 becomes 1, 0, right? And then we apply the control NOT gate. Control NOT gate is what? If your top qubit is 0, do nothing. So because this is 0, so do nothing to this. So 0, 0, still 0, 0. But if your top qubit is 1, apply the NOT gate to the lower qubit. So this is 1, apply NOT to it. So 1, 0 becomes 1, 1. And that is the entanglement gate I showed you earlier. Remember 0, 0 plus 1, 1, or a spin up plus spin down, spin down. Okay, I know I'm going a little bit fast because I want to give you an overview. It's difficult to understand or grab everything right away if you've never seen that before. But what I'm trying to show you is that what is a quantum gate and why it's important to have a 1 qubit gate and an entanglement gate. Okay, so this will come to the summary of the algorithm part, right? So I want to say one thing on the left. For a logical gate, it's not reversible. If I give you 1, 1, 1 as the output, I say the gate is a NAND gate. You don't know what the inputs are because 0, 0, 0, 1, 1, 0 all give me 1. However, quantum gates needs to be reversible. This is a CNOT gate. If you tell me the output is 1, 1, and I know this is CNOT gate, I know the input must be 1, 0. And it is easy to understand because this is not a dissipative process. It doesn't lose energy. You're just changing the state. You are just rotating the state. So you can rotate to one direction. You definitely can rotate back to another direction because it doesn't lose energy, right? So there is a check for something, whether something is quantum gate. If someone come to you say he or she discover a very useful quantum gate, super efficient, but you find that it's not reversible, you know that something is wrong. So what is a quantum circuit? At least for superconducting qubit, spin ion, or trap ion, it is like this. You have a state, boring function. You apply gates to it, another gates, and finally you do a measurement to get the result. In this process, you can always go back because you just apply the inverse gate, then you will go back to previous state. But in this process, this is the flow of time, remember. So when in the future you see some algorithms say you need to apply 1 trillion qubit, don't worry about the size of the chip. The size of the chip depends on the number of qubit, right? If you have 100 qubit, you just need the space for 100 qubit. But what is difficult is that you need to shoot microwave pulse or laser pulse for 1 trillion times. And that is what you need to take into account for a quantum computing algorithm, whether it's going to be efficient. Because if every gate time is 200 nanoseconds, if you need 1 trillion pulse, how long is it going to take? You need to take that into account. Okay. Actually, one more thing, I forgot about this error correction. Now, in classical communication or classical computer, whenever you have error, we can do error correction. A very common way is to do the repetition code, right? If it is 0, I just put 30, for example. So even there's a flipping becomes 001, I use majority vote, then I know this is still 0. And same for 1. And if you want to increase the accuracy, just add more 0, right? So the code space will just change. And that is a very good error correction. But unfortunately, you cannot do that for quantum computer directly due to two things. One thing is we already mentioned earlier, is that how do you copy something if you don't know the information, right? You will measure it and then copy, right? But in quantum computing, we say there's no cloning theorem. You just cannot copy arbitrary state. If you know what the state is, you can copy. But you are not really copying. You are just creating. You're just manufacturing, right? But if you give me a qubit, I don't know what the state is, I won't be able to copy anything. And that is the no cloning theorem. So because of this, I cannot use this repetition code directly. That's the first thing, right? So, and of course, when you try, you say, let me measure it then, but you cannot, because if you measure it, it's going to collapse. You lose the state. So you're not really copying, right? You damage the original one. So what we do is something called syndrome measurement. So what we do is, let's say psi is the qubit we want, it has the information we want. We do some entanglement. This is the control NOT gate with some auxiliary qubit or ancillary qubit. These are not the qubit we want, but they are very important. We entangle them, and then so that they have some correlation. When they go through an error channel, right? Or this just means that they got flipped or due to some error, and you come out, we can do some measurement. Right here is a simplified version of measuring. Combine measurement and correction together. We just measure the ancillary qubit. Based on what happened to ancillary qubit, we will know what had happened to the original qubit, and then we apply the appropriate correction. This cannot illustrate it, but you trust me, it is just like this. For example, if I see that this qubit got flipped to certain value, then I will know that, okay, my original qubit actually got a flipping also. If this lose the phase, I know my original qubit lose the phase also. Then what I do is I'm not going to measure my qubit. I just change the phase by applying some correction. Okay? Okay, so maybe I can, if there's any quick question, I can ask, maybe pause for 3 minutes or so to answer question. If no, I will go to the introduction to the hardware part. Is there any questions that I should answer now?
I think I can understand.
Oh. Okay. Okay, we don't measure, so this is the qubit we want, but we don't measure it. We measure the ancillary qubit or auxiliary qubit that is entangled to it. So we are actually measuring this one, so we don't damage the original one. But based on what happened to this ancillary qubit, I will know what happened to this qubit. So I will apply a correction directly. Does it make sense? Okay, so this is not a basic, and so okay, so well, I discussed entangle earlier by saying this is just a simple entanglement, right? But in that one, actually, it's more complicated. So we will not collapse the previous one. Yeah, so that's a very good question. Yes. Yeah, so the point is, like what you said, no matter what we measure here, we should not destroy the original state. Yeah. If no question, then I will just go ahead and we have more question at the end. Okay, so now we see in terms of algorithm, pretty simple, right? But then how do we implement it? There are many different types of hardware. Here I choose superconducting qubit because I work more on this for my research, and also it's also a very good illustration. But before that, I want to say there's something called DiVincenzo's criteria. So you can think of many things to implement a quantum computer, right? Even you can think about, can I use coins to build a quantum computer? So DiVincenzo gave 5 necessary criteria for hardware that can be used for a quantum computer. First, you need to have a well-characterized two-level system. Okay, this is understandable because we work on 2 states, right? 0 and 1, and their superposition. But one more important thing you will see later in superconducting qubit is that you might actually have multi-level. You actually need to make sure that it won't be excited to a higher level, right? So you need to maintain it at 2-level system. Second, you should be able to initialize it. Maybe I also jump to here and measure it easily, right? These are something we take it for granted for classical computer. Initialization and measurement should be very easy. But it is not the case because these are all quantum mechanical system. It's not guaranteed, but we need to make sure that. And another important thing is in classical computer, we seldom will initialize something. When we do computation, just start and then go all the way to the end. But we do a lot of initialization in many quantum algorithms because for many algorithms, you need to do measurement and then go to the next step and do initialization, etc. And error correction also need a lot of initialization. Just look at this. Once I correct something, I need to prepare new ancillary qubit to entangle it and continue to correct because the error will keep coming in, right? So it's not straightforward. So your initial time is also important. If you need to take 1 hour to initialize a qubit, it's not going to work. Another tool is that you need to have a long enough decoherence time, right? Because they're quantum object, they lose their information very quick. So you need to be much longer than a gate time. Now we already mentioned what is a gate. It's just a microwave pulse, a laser pulse. So the pulse need to have a certain length, maybe 200 nanosecond or 1 microsecond. Then your decoherence time need to be long enough. Your decoherence time is like only 10 nanosecond. Nothing can be done, right? Finally, I mentioned this before, you should be able to implement 1 qubit gates and an entanglement gates to build a so-called universal set of quantum computers. So how do we implement it? Well, this is just for fun, my mood, right? You ask me, what's my feeling today? 90% happy, 10% sad, right? Maybe happy because I can give this talk. Sad is that I need to have a lunch later, for example. But it's not a reliable qubit. So we can use spin, electron spin. You put an electron spin in an external magnetic field, then they have 2 energy levels, right? That is great. So I can have a state that's a linear combination of spin down and spin up. Or a photonic qubit. Here, I did not draw it. I mean, this paper did not draw it, but basically what it means is that there's something called dual rail encoding. If the photon is on the top path, then it is state 1. If it's at a bottom path, then it's state 0. If you don't observe it, it can be a combination, a linear superposition of up and down. This is something we always heard in quantum mechanics, right? I can be in this room, or actually I 10 to the power negative 20 chance I am actually in Texas. Actually, right? That is my wave function does has that probability. And or superconducting qubit. Here show an example, something called Josephson junction. We'll talk about that later. Treat it as a capacitor now. Actually, it's an inductor, but this is an island, but it's also a capacitor. So we try to ask how many extra Cooper pairs. Cooper pairs is just a pair of electrons in this island. Maybe 0 extra or 1 extra. And their superposition becomes the quantum state, and that is something called the superconducting charge qubit, right? Now, then you can imagine they are all quantum objects, right? Except for photonic qubits. This one I can work at room temperature, but for others, they very small energy separation, and that's why I do need to have to cool them to very low temperature. Otherwise, they will lose the noise. They will lose the information due to noise, right? So here show an energy landscape. Many of you are familiar with that, right? Circuit designer, you know that it's 26 millivolt at room temperature for the thermal energy, right? Mini EV, right? But your qubit separation is so low, it corresponds to only 0.23 Kelvin. Right, very low energy. So that's why we need to put it in dilution refrigerator to cool them down to 10 millikelvin for spin qubit and superconducting qubit. Right. Otherwise, you might have flipping. You will excited state becomes 0. You will have a superposition, lose your phase. You will 0 plus 1 now become maybe 0 minus 1, 0 plus I1. And this is a typical T1 time, flipping time, right? That is like about 200 microseconds. And this one is a measurement to find the T2 time, which is the dephasing time, is about 20 microseconds, right? So you can see how short the gate pulse needs to be, right? Just to give you an idea. So how do we implement a quantum computer using a superconducting qubit? Now, this is the audience that I don't need to explain anything about this, right? You are all very good in circuit. This is just an LC tank. So for LC tank, it's just a simple harmonic oscillator, just like a mechanical simple harmonic oscillator. If you cool it down to very low temperature, it has some quantum mechanical behavior. The number of energy it can store actually is discrete. And it's just like a simple harmonic oscillator. You can have 0 photon. Again, you know photon just electromagnetic wave. It's just talking about the energy package that you have. right? So you have 0 photon, 1 photon, 2 photon. The problem is that there's energy separation. It's the same. So if I call this qubit state 0, this is state 1, this will be state 2. And it will be easy for me to excite the qubit to state 2, and then that violates the differential criteria. Because now I will compute outside of my Hilbert space, 0 and 1. That is not good, right? So we have something called Cooper pairs, and before that, I just remind you that we are going to talk about Josephson junction for superconducting, but just want to remind you something called Cooper pairs. When you cool the electron to very, very low temperature, cool the metal to very low temperature, it becomes superconducting. What happens is the electron will pair together, and they are called Cooper pairs. And the important thing is that because they're Cooper pair, their spin is 0. In the past, in chemistry, we know that electron are fermion, they cannot occupy the same state. But now they are Cooper pairs. Then they are spin 0, they become something called boson, just like the night. The photons, they can have the same state. So at superconducting state, they all have the same state, and we can describe it by using a wave function and by using one parameter, the phase of this army. They have the same state, just like a marching army. They all in the same phase, right? So we can describe them with the phase. And that's why there's something called Josephson junction. Look like a capacitor. Indeed, it is just superconductor, insulator, superconductor. And as I told you earlier, because they're superconducting, all the electrons, they become a macroscopic quantum object. They have the same phase. I call it phi A. The bottom one, they have the same phase. I call it phi B. I only need these two parameters to describe this quantum object. And there will be tunneling between them due to quantum mechanical tunneling. And then we have something called Josephson equation. Now, because of time, I don't go into details. But the main point is that its current will depend on the phase difference. And that its voltage will depend on the rates of change of the phase, right? But if you go through all this equation, eventually find that it has inductance. And the inductance is nonlinear. That is the critical part. So a Josephson junction gives you a nonlinear inductance because you see that the inductance depends on the phase difference between them. And they also have the associated energy, which is also which depends on phase, right? Now, a lot of things. The only thing I want you to take home is that there's something called Josephson junction, very simple superconductor, insulator, superconductor. And just due to the superconducting theory, they are nonlinear inductor. Okay? Then what? Because they're nonlinear, I replace the LC tanks inductor by Josephson junction. So instead of this inductor, now it becomes Josephson junction. So now it's a Josephson junction in parallel with a capacitor. And what will happen to the energy landscape? When it was linear, you have a parabolic landscape. But now because your energy depends on cosine phi, you see that it's a cosine landscape. So it has so-called anharmonicity. Now the discretized quantized level are not equally spaced. So I have 0 stay here, 1 stay here, 2 stay here, and the separation is much larger at 0 to 1. So if I apply a microwave pulse to it, then it will only oscillate between these two because the energy cannot promote it to another level. Okay, so just want to tell you that's why Josephson junction is used in superconducting qubit, because we want to form the well-separated two-level system. That is the major reason. Okay, so now we have two-level system. How do we form the single qubit gate? This is, again, we don't need to go to the math. It's not important. The most important thing is I want to remind you that some already know. For rotation, if you want to rotate on a broad sphere, right? This sphere is embedded in our real space, so the rotation is still just like how we rotate in the real space, right? If I want to go from one point to another point, I only need to make sure that I can rotate it about 2 axes, because this is called Euler rotation, right? So no matter what, let's say you want to fly from let's say San Francisco to Brazil, to where, let's say to let's say Tokyo, right? So I can also, like, I forgot the latitude and longitude, but you don't need to fly directly to Tokyo. You can maybe fly horizontally to a place, maybe Hawaii, I don't know, or Korea, and then within Korea you go north a little bit and then fly to the west again, right? So just not a good analogy, but after all, a rotation from any point to any point on this broad sphere can be decomposed into a rotation about this axis, and then another rotation about this axis, and then another rotation about this axis. So the point here is that I need to be able to do this type of rotation. And here, no need to worry about this. I just want to show you that when you rotate this, in physics, it's related to something called Pauli matrix, sigma x, sigma y, sigma z. Okay? Why do I want to say this? This is a circuit to do 1 qubit gate for the transmon qubit. Here is the transmon qubit again. This is the inductor. This is the Josephson junction. This is the capacitor. So you have a two-level system here. To do the rotation, all I need to do is just couple it with a capacitor and generate a special pulse. This is a microwave pulse. It has an envelope S of t. It has a frequency omega 1. It also has an initial phase phi. Now, if you go through the derivation of the quantum mechanical derivation, what we call circuit quantization, right? That's in my book. I do it step by step. You will find that this will give you an interaction Hamiltonian, or how this transmon qubit is going to change of this form. And this form, as I said earlier, if you have a sigma c, right, Pauli matrix sigma c, then you will be able to rotate it about the z-axis. If you have y, you will be able to rotate it about the y-axis, as I show here, right? And you trust me that you work. And then how fast it rotates, what is the angle it rotates, completely depends on omega 1 phi and omega r. And all these things are what? Circuit elements and the pulse, including the phase control, right? What is the phase of your pulse? What is the total capacitance of the circuit? What is the gate capacitance? What is the pulse shape? So that's why I say circuit designer and microwave engineer control 90% of a superconducting or any quantum computer, because this is just a boring qubit and you are sending this pulse to it. And you can imagine any error you make in this arbitrary waveform generator, mixer, or local oscillator, phase noise are going to affect the quantum computing result. And how do we do a 2-qubit system? Again, we don't go to the math. I just want to show you that this is a qubit 1, qubit 2. They originally have different frequency, right? The frequency I'm talking about is the ground state and excited state energy difference, 0 and 1. So they don't talk to each other. What we do is use something called flux tunable qubit, which we did not discuss. But this qubit will depend on the flux passing through the loop. And again, this is something you know very well as a microwave engineer. You tune the flux, then they will what? Talk to each other. This is a simple one, a simple capacitive coupling. Through this communication or interaction, you eventually can come up with some change of the state, and that gives you an entanglement gate. Now, this entanglement gate is called I-swap gate. It's not the C0 gate I mentioned earlier. That is because for different quantum computing architecture, they have different physics. And for superconducting qubit, it cannot implement C0 gate easily. So we say that they are not their native gate. It can do I-swap gate easily. Another is called echo resonant, I forgot the name, that is used by IBM-Q, right? They all have their drawback and pros and cons, but just remember different type of gates are needed, right? But again, what is the role of a circuit engineer? Again, this gate is completely controlled when you turn on this flux and how you engineer the coupling. And all this, again, flux noise, phase noise, charge noise are going to have an effect, right? And here, just to prove what I said earlier, if you I did not say it actually. I swap gate is just the same as a C0 gate. This is a C0 gate. If I want to implement a C0 gate using I swap gate, I need many 1 qubit, 2 I swap gate, and some 1 qubit gates. Then they are equivalent. Okay. Okay. So now let me step back. I still spend five more minutes. Just step back to see what does the system look like. You see that. In a quantum computer, you do Python programming, you have a lot of FPGA, a lot of arbitrary waveform generator, and eventually you create the S of t, the envelope function that I mentioned earlier. You will then go through the mixer with the local oscillator at room temperature because they are bulky. This can have GPU or etc. because to do error correction. They send this signal and through this attenuator to remove the thermal noise, and eventually you reach the qubit and the resonator coupled to a qubit. Then the qubit receives your signal. Then you compute a quantum gate. If you have another gate, just keep sending your pulse. Now, when I want to read out, I may have another path because I need a different frequency for read out. I did not discuss here. So, but again, I just send it to a higher band, higher frequency. Again, go for attenuation. Then you go to a resonator. This resonator is coupled to a qubit. Then it got reflected. And then I go through this amplification train and analyze the signal coming from there. Then I will know whether it's 0 or 1. So here I want to talk about, and this maybe I'll go quickly, right? This is just to say that, to remind you that, hey, in order to generate this 1 qubit gates, I just need to have this I port and Q port, use IQ quadrature, in phase and quadrature, right? And then just generate the correct complementary signal, go through oscillator, then I will get this, right? I'm sure you are all expert better than me. So there's no problem for sending out the signal. How do we do the readout? So I want to spend a little bit time on this. This is just a microwave circuit. If you shoot in a microwave pulse at different frequency, you have different S21, right? You have depends on the circuit. So this is interrupted by a resonator. So you can imagine only the microwave pulse that has the frequency as the resonant frequency will go through. So if you sweep the frequency, you will see a peak in S21. Now it turns out that if you couple this resonator to the qubit, the resonance frequency will depend on the state of the qubit. If the qubit is 1, then the resonance frequency will be lower. The qubit is 0, the resonance frequency will be higher, right? So because of this, I will then just shoot a pulse to here to see how the phase is changed. So let me show you the plot. So again, if you sweep the frequency, you just measure the magnitude of S21, you will see a peak. And when it is excited state, because something called cross-cut, that what we just talked about, it changed the resonant frequency of the resonator. You have a lower resonant frequency. Ground state has a higher resonant frequency. If you plot the imaginary and the real part, let's say this solid line is the real part, then you will see that, yeah, for the dash line, they are the same, they are about 0. If I shoot in a frequency of the original resonant frequency. But if it is ground state, I got a positive real part. If it is in excited state, I get a negative real part. So basically, this is just to detect the phase of the signal coming out from the transmission line, right? So based on this, then I know whether it's 0 or 1, right? So if it is positive, then I notice it's 0. It's negative, I know it is 1. Well, I can do some transformation. We call it IQ block. Then you will have excited state and ground state here. You just need to measure its position in this IQ plot, right? But you don't see that now. I make a circle. We call it IQ blocks. Why? That is because of noise, right? You don't just get 2 points. If it's clearly 2 points, that is great. It's easy to distinguish. But with noise, if you don't design it well, the crosscut is not large enough, right? Means the shift is not large enough, or you have a lot of noise, then even for ground state, you will get some positive part, you will get some signal in the first quadrant, right? So if you get a point here, you actually don't know whether it's 0 or 1, and that is the so-called readout noise. Okay, so I still have 7 minutes, so I think that's all I want to say. I hope that I give you an overview of the algorithm and also the hardware, and electrical engineer, particular for microwave and analog circuit designer, play a very important role. Okay, please let me know if you have any questions.